So this is the Earth Part 2. We're going to talk a little bit about atmosphere and the magnetosphere and other aspects of the Earth. So the Earth's magnetic field is generated by its core, really. The outer core is liquid and the inner core is solid. And the inner core is spinning inside the outer core, and that spinning generates friction, which separates charges the way you separate charges when you rub your shoes on the carpet and touch something. And those charges then are spinning with the Earth as the Earth spins, and that generates a magnetic field. This process is kind of similar to the way electric motors generate magnetic fields. If you ever look at an electric motor, and there are more and more of them nowadays, they're just coils of wire that you run current through, and they generate a magnetic field that way, and that interacts with magnets, actual magnets you have around the motor, and that process causes the spinning that occurs in a motor. The Earth and other objects are kind of generate magnetic fields a little differently, but it's the same principle. The Earth separates charges, and the spinning of the Earth produces a magnetic field as a result of that, and that's where it comes from. For this to happen, the Earth has to have liquid in its interior so that these things can rub past each other and there can be friction and so on. And so celestial objects that have significant magnetic fields, it tells us they have active geology, some kind of molten stuff going on in their interior, and that's a clue about other planets and moons, for example, which we'll talk about later. The Moon, Mercury, and Mars all seem to have cooled off enough that their interiors are solid and they don't have significant magnetic fields, none of them, just very tiny ones. Venus has an active geology, but it's not really spinning. Venus's day is like 220 Earth days. It turns very slow on its axis, and so it's not doing much spinning. So it doesn't have a magnetic field because it's not spinning, or it doesn't have a significant one. So back to the Earth's magnetic field. It turns out it's really important for us. This is a cross-sectional view of the Earth's magnetosphere. It's kind of like a way of saying atmosphere, but with magnetism. It's the zone of the Earth's magnetic influence, you might say. And it turns out that this is actually really important for planets that want to keep their atmosphere and these high energy particles from the sun from hitting us. It turns out in this picture you see that there's this thing called the solar wind. The sun is very hot and it's blowing out high energy particles all the time. It's just, they call it the solar wind. It's just spewing out particles. Well, it turns out that this magnetosphere protects us in a variety of ways from the solar wind. These would be very dangerous gamma ray type particles that would be hitting us in our atmosphere and so on. And the magnetosphere kind of acts like, you can think of it as a rock in a stream or something like that. It pushes the particles out of the way, or just absorbs them, slows them way down. These particles from the sun are not dangerous in and of themselves, really. They're like iron ions or hydrogen ions or something like that. It's the dangerous in that they're going really fast. A baseball isn't dangerous unless it's coming at you really fast. And so the magnetosphere both pushes them out of the way and slows them down to the point that they're not dangerous. And so that's how it protects our atmosphere and us in it. I'll talk more about that in a minute. Let me just go to the next page. So the solar wind is a constant stream of highly energetic particles. The sun is constantly spewing these off. Nevertheless, the sun only loses a tiny fraction of its life. You might think, well, it's going to lose all its mass. Well, no. The magnetosphere protects us from it. If we didn't have the magnetosphere, our atmosphere would kind of be sandblasted away by these, over a very long period of time, by these particles from the sun. And so it kind of protects us. The word magnetopause is just, let me just page up really fast. So here it is up here. It's just kind of the boundary of the magnetosphere. Van Allen belts, or regions of highly energetic particles, get trapped, and they're not too well understood, the Van Allen belts, and so I don't know a lot about them, except they're regions where these high energy particles get trapped inside the Earth's magnetic field in these belts around the Earth. And they're studied at various levels. They get bigger or smaller and change shape and do all kinds of things. Okay, let's talk about the Earth's atmosphere. There's a lot to unpack here. Here's a picture on the right, and a few things you should know. The troposphere, if you look here on the right, the lowest layer is the troposphere, and then the stratosphere, and then the mesosphere, and then the ionosphere. As you go up, I'll talk more about them in detail as we go. This red curve here is kind of interesting because it's the temperature. So if you look at the bottom axis, the x-axis across the bottom, it's the temperature in Kelvin. You don't need to know Kelvin scale. You just need to know that to the right is warmer and to the left is cooler. And so you notice that the troposphere is warmest at the bottom, but the stratosphere is warmest at the top, and so on. The ionosphere warms up at the top. And so we'll talk about those as we go, why this temperature curve looks the way it does. You can kind of see where the clouds are and so on. The height is on the left, and this is in kilometers. You can kind of call that miles. You might divide by 2 and do miles. A kilometer is about 6/10 of a mile. So this 50 is really about 30 miles, and this 100 is really about 60 miles. I don't want to get too caught up in the exact distances. I'll tell you what they are in miles in a minute. The troposphere is about 8 miles high, something like that. And so on this scale, it ends somewhere around where these clouds are, I would say. All right. So the troposphere is the lowest layer in the atmosphere, about 0 to 8 miles. All the weather happens in the troposphere, or nearly all. I think in Oklahoma, we sometimes get clouds in our thunderstorms that rise into the stratosphere. But for practical purposes, all the weather happens in the troposphere. Temperatures average from 70 on the bottom to minus 80 at the top. So it's warmer at the bottom than at the top. Also, the troposphere has about, about 85% of the total mass. Let me just pack this up a second. So 85 to 90% of the mass of the atmosphere is below this line here, below the clouds, or from the clouds down. And that's because the air is much more compressed down here. The weight of the air above is sitting on top of the air below. And so the atmosphere is much more compressed at the bottom than at the top. It's nearly a vacuum up here in the ionosphere. So the troposphere is heated from the ground up. What that means is that the temperature is highest at the bottom, which we already saw. The reason for that is because the sun's energy passes right through the air. Most of the sun's energy comes in the visible light range, and the air is transparent to that. And so the sun's energy goes all the way to the ground. It heats the ground. We're well aware of that here in Oklahoma. And then the ground heats the air, and then the air heats from the ground up. And so we could talk about convection and things like that. The air gets heated near the ground, that rises and warms the atmosphere up at the higher elevations, at the higher altitudes, but it's not enough to make it as hot as it is at the bottom. So it's hot at the bottom, and then it's cooler as you go up. That's the troposphere. The stratosphere goes from about 8 to 30 miles. And notice it goes from about minus 80 degrees Fahrenheit from the top of the troposphere to about 40 degrees Fahrenheit. So it warms up. The reason it warms up is because the stratosphere contains the ozone layer. Ozone is O3, and it turns out this ozone layer protects us from ultraviolet light. The ozone layer in the stratosphere absorbs ultraviolet light. The atmosphere and the magnetosphere do a lot to protect us from very dangerous high-energy particles from the sun. And so the reason the stratosphere increases in temperature as you go up is because the top of it is getting more ultraviolet light than the bottom of it. And so it's getting heated at the top more than it's getting heated at the bottom. And so it warms as you go up. It turns out there's a hole in the ozone layer that's been caused by pollutants. This has been worked on through global efforts for 40 years now, and some progress has been made, at least efforts to bring the increasing size of the hole to a stop. It would be bad if we lost the ozone layer. Just as a side note, ozone, you might think, well, ozone is O3, that's just oxygen. Can we breathe it? No, you need O2 to breathe, not O3. O3 is not breathable, or at least we can't metabolize it. Ozone is often created by industry, and it's a pollutant at the Earth's surface. So you'll sometimes hear ozone layers levels are high in large cities like Los Angeles or something on particular days, and don't go outside or something like that. So it's good when it's in the upper atmosphere. It's bad when it's on the ground. What's destroying it in the upper atmosphere is pollutants we're creating, often by one of the big ones is coolants that are used, like the reason we don't use Freon anymore as a refrigerant for cars is because it was found to be one of the culprits in destroying the ozone layer. So that was the stratosphere. The mesosphere goes from 30 to 50 miles, and it cools back down. It goes from 40 at the bottom to minus 100 at the top. That's where most meteors burn up. I don't know if you know about shooting stars, but when you see them, they look like another star, any star, but they're moving. Well, they're really not. They're the size typically of a grain of sand. There's just a meteor or a piece of dust that's coming into the atmosphere at a high speed, and so they burn up, typically in the mesosphere. And then the ionosphere is above that. It goes for about 50 to 100 miles. And it's minus 100 degrees Fahrenheit at the bottom. And once again, it gets heated at the top. It's mostly absorbing higher energy particles like X-rays. And so it's warmer at the top than at the bottom. It's similar to the ozone layer in the sense that it's absorbing certain radiation from the sun and heating up. It's practically vacuum. We can have spacecraft in orbit at 100 miles. And so there's not much matter in the ionosphere. It has some social importance in the sense that it has lots of ions. Because of all these X-rays, atoms absorb X-rays and become ionized. Those electrons in the atoms get this huge boost of energy, and they just get thrown out of the atom completely, and creates ions. And it turns out you can bounce radio waves off of the ionosphere when the sun's shining on it, and so that allows people to bounce radio waves around the world, and so talk on shortwave radios for very long distances. So amateur radio enthusiasts love that sort of thing. Okay. So let's talk a little bit about climate, since we're talking about the atmosphere. There are four major factors that can lead to long-term climate change. They're basically solar brightening. It turns out as the sun is aging, it's slowly getting brighter. This increases the amount of energy it's releasing. Also, on a shorter time scale, the sun goes through a sunspot cycle in which its energy output is varying slowly by a percent or so. And so we can get hot sunspot cycles and cool sunspot cycles, and you can dig into that stuff pretty deep. The climatologists are all very much aware of these things and are monitoring these things, because everybody's, at least for the last 30 years or so, has been really interested in the climate and what factors influence it. Also, things that can influence long-term climate is the changes in the Earth's axis tilt. These things happen and are understood by physicists that the tilt of the Earth's axis relative to the plane of its orbit varies slightly over time, and this affects ice ages, as it turns out. The bigger the tilt, the fewer the ice ages. The smaller the tilt, the more. If the Earth is tilted more, that means the sun is looking at the poles more, and that means that it melts the polar caps, and it can increase the melting of the polar caps and make the polar caps a little smaller, and that reduces the possibility of ice ages. There can also be changes in the Earth's reflectivity. If there are more clouds or there's more snow on the ground, the Earth isn't absorbing as much sunlight. That light is going right back into space. And so these are things that affect the Earth's long-term climate. And finally, changes in greenhouse gas abundance. This is where humans come in. We are making significant changes in the amount of greenhouse gas on the planet. And so that can affect the surface temperatures. So let's talk about the greenhouse effect for a minute. Hopefully we all understand what that is, but let's just talk about it anyway. Anyone who has parked a car in the sun on a summer day understands the greenhouse effect. The science is that visible light passes through the glass. It's absorbed by the materials inside the car, and then it's re-emitted as infrared light, which cannot pass back through the gas, so it's trapped inside your car. So your car heats up. That's how greenhouses work as well. The atmosphere is a little more complicated than that, but you can kind of draw a comparison to it. It turns out the atmosphere is transparent to visible light. We know that because the sunlight makes it all the way to the ground, right? But it's somewhat opaque to the infrared. Not fully opaque, but somewhat opaque. So when the sun shines on the Earth, visible light makes it all the way to the surface. It heats the ground warms up, and when a warm object emits radiation, it's in the infrared. This emitted light would normally leave the planet, but the atmosphere doesn't let it do that, and so we heat up. If you've ever been in the desert or in the mountains, the Earth will cool off a lot faster at night. If you're at high elevation, it'll do that. But also if you're in an area where the humidity is really low, because water is a greenhouse gas. And so there are lots of ways to let infrared radiation escape faster, and there are also ways for it to let it not escape. And so when we're trapping greenhouse gases, when we're putting greenhouse gases into the atmosphere, we're trapping infrared radiation. If the Earth were a perfect black body, no atmosphere, just an object floating in space, the temperature where we are would be about minus 17 degrees Fahrenheit. But because of the greenhouse gas, because we have gases around our planet, because of the effect they have, the greenhouse effect, it turns out our average temperature on the planet is about 57 degrees. So this is a good thing. The atmosphere is trapping heat, and that makes the planet comfortable for us. The problem is when we add too much, we get too much of a good thing. And so the Earth we're now seeing increases in temperature that are raising concerns for us that if they continue, there'll be a problem with that. So it turns out CO2 isn't the only greenhouse gas the only gas that contributes to greenhouse warming. There are other gases that affect this. Methane, for example, you'll occasionally hear about that in the news. It turns out it's about 30 times more effective than CO2 for trapping heat. But there's a lot less of it, and it doesn't stay in the atmosphere as long, so it's not as big a factor as CO2 is. But these other gases, which you'll hear in the news, that's what they're talking about. They're talking about their ability to trap infrared radiation, and if their presence in the atmosphere is caused by us, and if it's increasing. So these are carbon dioxide levels since 1960. I'm trying to put things in here that are not really disputed. Climate change, global warming has sort of become a political thing, and so I'm trying to put in things that I think everybody kind of agrees on. The levels of carbon dioxide have been steadily rising for most of the last century. This is important because carbon dioxide is a greenhouse gas that traps heat in the atmosphere and warms the planet. If we get too much of it, it can be harmful for us. So historically, for the planet, most of the CO2 came from geologic processes like volcanoes. There's a CO2 cycle, which we'll talk about in a little bit. The problem is humans are now producing about 100 times more CO2 than sort of natural processes produce. And so that's a big number. A gallon of gas, which weighs about 6 pounds, produces about 20 pounds of CO2 when it's combusted. So you might think, well, how can a gallon of gas, 6 pounds of gasoline, produce 20 pounds of carbon dioxide? It's because the oxygen comes out of the atmosphere. All you're doing is pulling the carbons out. Combustion processes of gasoline produce carbon dioxide and water. So let me see if I can I switch this? Nope, apparently not. So there isn't really a simple chemical formula for fuel, but it contains carbons and hydrogens. That's what gasoline contains. If methane, for example, is CH4, well, there are several different molecules that comprise gasoline, but they're just carbons and hydrogens, and so the hydrogens grab an oxygen and make H2O, and the carbons grab oxygens and make CO2, and so it turns out these oxygens just come out of the air, which isn't a big deal because we have tons of oxygen in the air, and so they produce carbon dioxide and water. Well, these carbon dioxide, these oxygens are 16 times heavier than a hydrogen. So you end up with more mass of carbon dioxide than you started with mass of fuel. And so every gallon of gas produces about 20 pounds of carbon dioxide. And we use this type of process in heating homes, not just for cars, but in heating homes and all sorts of other things. So this is concerning. The steady rise in the amount of CO2 in the atmosphere is one of the things people are worried about. So it turns out there's a carbon dioxide cycle. Carbon dioxide is outgassed by volcanoes. This is not counting what's going on with humans. So if you look at what's going on the planet before humans came along, carbon dioxide is outgassed by volcanoes, and then it's washed out of the atmosphere by rain. So rain combines with the carbon dioxide, the water in the rain combines with the carbon dioxide, makes something called carbonic acid, which falls to the ground and gets washed into the water, and it forms sediment on ocean bottoms. It's a natural process. If there's too much, we get something called acid rain, and for other reasons that creates other types of problems. So it deposits in ocean bottoms and creates sediment in ocean bottoms. It turns out this just sort of becomes rock, this limestone, and it's recycled as a rock through tectonic processes. And so that's the carbon dioxide cycle. This rock then ends up in volcanoes, pulls CO2 back out of it, sends it up to the volcano, and the cycle continues, right? And so that's the carbon dioxide cycle. This cycle can act like a thermostat for the Earth, it turns out. If the Earth gets warmer for some reason, more water evaporates. That's what happens when the Earth heats up, water evaporates. This puts more water into the atmosphere, which produces more rain, which washes more CO2 out of the atmosphere, which traps less heat, which cools the Earth back off. And so if the Earth gets too hot, extra water in the atmosphere will wash more CO2 out, which will cool the Earth back down. If the Earth gets too cool, when it's cold out, there's less water in the air. Water condenses out of the air. That would produce more CO2 in the air because it's not getting washed out, and the Earth will warm back up. And so the CO2 cycle kind of acts to help regulate the surface temperature of the Earth. Occasionally we get ice ages. We talked earlier about the tilt of the Earth's axis or some effect from the sun. All these things can ultimately cause ice ages, and it takes a long time for the Earth to respond, the CO2 cycle, to fix this. But here's an example sort of how that happens. If the Earth cools off a few degrees and we get an ice age, the ice age can cover a lot of the planet all the way down to the equator. And as the ice builds up, it can be more reflective. Snow is more reflective, and so that makes the problem worse because the Earth isn't absorbing heat to warm back up. And so this can go on for a long time. We can get ice ages. We've had ice ages that have gone all the way down close to the equator at times, certainly well into the United States. These are geologic things. This isn't a recent concern. It's just understanding how the Earth works. Well, eventually, as it gets colder and colder, all the water leaves the atmosphere, or much of it does. And now these volcanoes, which continue to erupt because just from natural phenomena, build up more and more CO2 in the atmosphere. Ultimately, the CO2 will trap enough heat that it'll warm the Earth back up and pull it back out of an ice age. These are on sort of very long time scales, how the Earth's climate works. And have nothing to do with human activity. This is just a natural process for the Earth. Okay, let's talk a little bit about the rock cycle. So you could take a geology class and spend a whole semester studying rocks, and for me at least it would be really interesting. But we're just going to talk about three basic types of rocks. Sedimentary rocks, metamorphic rocks, and igneous rocks. And so igneous rocks are produced when magma comes above the ground, which makes it called lava, and solidifies. That's what an igneous rock is. It's just solidified lava. Now, this stuff gets on the ground and then undergoes erosion of some kind. Water erodes it, wind erodes it. There's all kinds of things that can erode it. Sunlight, just all kinds of things that can erode these igneous rocks. They get washed downstream and turned into sediment, right? That sediment piles up in stream beds or river beds or ocean bottoms, right? And by the way, we just talked about a type of sediment, right? When CO2 washes out of the atmosphere, it can form a limestone sediment on ocean bottoms. And so as that sediment builds up, the sediment that's way down below gets crushed and heated, mostly just crushed, compressed into rocks. And so you'll see sedimentary rocks. Sometimes you can see them just in the layers, like the Grand Canyon or something like that. If you go down far enough, you'll see rocks formed just from compressed sediment. And so igneous rocks, erosion, sedimentary rocks. Well, sedimentary rocks can be very deep down in the ground, where it can be hot, or there can be enormous pressures, and will change them into some other type of rock. And so instead of just being a sedimentary rock, they'll go through some process that some kind of chemical change or a textural change or something that'll make it into metamorphic rock like granite or something like that. And then those rocks can any of these rocks can get just recycled through a geologic process that will ultimately end them back up in igneous rocks again. So most of the rocks we see on the ground are some kind of are one of these categories. An igneous rock is a sedimentary rock or a metamorphic rock. Metamorphic rock is one of these two guys that's had its form changed somehow. Either an igneous rock that's somehow gotten compressed or heated or something that's changed its form, made it a different rock, or the same thing could have happened to a sedimentary rock. So igneous rocks were rocks that are formed from lava. We see lots of these where seafloor spreading occurs, or just near volcanic areas, or anywhere else for that matter. Sedimentary rocks are produced by the action of the wind, water, and ice. Minerals that precipitate on ocean floors or in plains over long periods of time, and usually after they're buried into large depths, form sedimentary rocks. A metamorphic rock is an igneous rock or a sedimentary rock which has been subject to high pressure or heat or both. This can happen in various types of tectonic or geologic events. Often sedimentary rocks are found to be vertical, so sometimes you'll see layers of rocks. Those are like sedimentary rocks, geologic strata, but they'll be tilted at crazy angles. This tells us that some kind of upheaval has happened because sediment lays down horizontally not at an angle. And so they're clues to what sort of geologic activity has occurred. So we can talk a little bit about a rock life cycle. So we talked a little bit about how rocks go through these different phases, but we usually say anytime a rock has been melted, its life, if we can use that metaphor, has ended, and it's becoming a new rock. We can age a rock through radioactivity techniques. It's called radiometric dating. But once it's liquefied, its clock gets reset. Rocks get recycled through various geologic events. Sedimentary rocks on oceanic plates get subducted under continental plates and melted, then recycled into igneous rocks, and so on. The typical age for an Earth rock is 50 to 100 million years. There are rocks that are 3 billion years old. There are rocks that are a few thousand years old, or less even on Earth. But an average age for a rock is around 50 to 100 million years. And what this means is that the Earth's active geology is recycling rocks on roughly this time scale. This is clearly a lot younger than the age of the Earth. There's a lot of active geology going on the planet. The Earth's age is about 4.57 billion years. And here are some questions. And so maybe I'll just skim through those. I just have questions on the magnetosphere. You should be able to just look back at the material in the chapter and in the section and follow the text and be able to answer most of these questions.